Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. Okay, today's little mini lecture, we are going to look at 3 groundbreaking historical experiments around the early 1900s that were really foundational towards our modern view of the atom. We're going to start with J.J. Thomson in 1897 and looking at the cathode ray tube. One of the big accomplishments he had was actually getting a better vacuum so he could do better experiments. So sometimes it's these small breakthroughs that make a big difference. Okay, so what's a cathode ray tube? Well, if you're really old like me and you remember when there were dinosaurs, you probably also remember when there were tubes with your TV. Or you may have seen a neon sign. That's probably a better example. So that's a cathode ray tube. What do we really... You got a negative end, you got a positive end, and particles flow across. And you can do fluorescence and things like that. So you can see that. You can put a detector here. Practical applications. I'm not going to worry about that. But we got a vacuum tube with particles flowing across. And there was some discussion at the time of whether these are best thought of as being made of particles shooting across, or whether it is a wave, like light, coming from the sun. The fact that I travel only in straight lines implied wave behavior. The fact that it was really a focused beam kind of seemed like it was a particle. Light didn't scatter out. And Thomson set about trying to separate the two pieces and seeing if there was a difference there. So he had this tube, and the first thing he did was he put a magnet there. So if you put a magnet next to this, what you see is the tube bends towards the magnet. And of course, if you reverse direction of the magnet, you can bend the tube the other way. And it implied that it had a charge. So this was a charged particle. Next thing he did was he did the same idea, but he put a charged plate. So he put, it doesn't really matter which side's positive, which side's negative. We'll put positive up here, negative here. And this also bent the red. So this also did the same thing. I'll redraw it just so you can see a different bend. And this in and of itself was a major accomplishment to show that there's a negatively charged particle and it's traveling like a wave. Okay. But what he did that was really breakthrough was this third part. He was able to calculate the charge to mass ratio. And he found that this ratio was astronomically large, which implies, of course, 2 things. Either that the charge is astronomically large, or that the mass is really, really tiny. We're probably not made of things with massive, massive charge. We'd notice that there'd be some bad implications to that, so we took the opposite approach. What if we had a reasonable charge but the mass was small? Then the assumption is that this particle with a negative charge is much, 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 much smaller than a hydrogen atom. So, from Thomson, we know the existence of a negative particle, and you could also assume a positive particle, since we know that you're made up of mostly neutral things, and this has to be made up of neutral things. If this was made up of all positives, they would repel and explode apart. If you could Harry Potter up a jar of positive charges, there'd be a crater with the explosive force of them repelling each other. This is likewise, it's not made of all negative things because they would repel each other. So we know that this is made of neutral, anything you can touch. My hair, my glasses, this board. You know it's made up of neutral pieces. It can't be made up of all positives or all negatives. So the overall charge has got to be neutral. So if there's something that's negative, there must be something that's positive. Okay. And we know they're smaller than an atom. So there's 2. So this is the fundamental things that build up of an atom. Okay. So let's go to Millikan, 1909. So we're going to fast forward a dozen years. All right. So this is supposed to be a can with 3 layers to it. So we're going to take a nebulizer, fancy word for, perfume bottle, cologne bottle. You're going to spray it out so you get really fine mist. That's called nebulizing. All right, so we got our little nebulizer. We got little oil droplets. And some of those oil droplets, as you squirt them, if you cut a hole in the middle of the plate, some of those droplets are going to fall right through the hole. That makes sense. Just statistically speaking, most of them will coat the side, but some of them are going to fall through. So if we make a little ocular device, little hole there so we can take a look. There's a beautiful blue eye. Looking through at the droplet, the droplets are going to fall through. Now, what's interesting is the droplets seem to have a negative charge. So if we do the same thing with a positive plate on top, negative plate on the bottom, negatives and negatives repel. So you can crank up or down this amount of charge. We can vary that. And what this will do is, if you do it just right, you can actually get it so that droplets will hover in midair. Then we know that the gravitational force pulling down is the same as the electrostatic repulsive force pushing up, and you can calculate the actual charge on that droplet. So he's able to calculate the charge on the droplet, and he noticed that it was a multiple of the same number. I won't give you numbers, but I really would love you to think about how we actually do science. So you'd graph the numbers, right? Maybe you'd graph the numbers and you would see these little, it's not going to be perfect data, so you get these dispersed things at equal distances. Well, you would think, well, this might be 1 charge piece, 2 charge piece, 3 charge piece, and you take that multiple, and that's the fundamental charge. So he's able to get that 1.6 times 10 to the minus 19 coulombs as the charge of that negative particle Thomson demonstrated the existence of. So we now know the charge. If you remember, he had the mass to charge ratio, so put the two pieces together and we can get the mass of an electron. So we have the mass of the negative charge, we have the charge of the negative charge. So we've kind of figured out where the negatives are, and I like personally to be a positive person. You can get more out of life if you try to look at the positive side of things. So, enough of the negativity. Let's move over to something more scrumptious. The plum pudding model. All right, maybe exaggeration, but still. So this is known as the plum pudding model, that we just, you had pudding, that's your atom, and then, there are plums within the pudding, and that might be a positive charge or a negative charge, and they're just dispersed through there willy-nilly. Okay, so Rutherford, 2 years later, 1911, did the gold foil experiment. So we took a radioactive piece of rock, pitch blende, something like that, put it in a container, put a slit through there so that only the particles being shot out, which are alpha particles, are only going in one direction. What do we know about these alpha particles? They have a lot of mass, and they're positively charged. So that's probably important. So this is massive, and it has a positive charge. Okay, so we took a really, really, really thin sheet of gold foil and placed it here, put film, so you want to take the original Kodak film paper, and put that around. So anywhere the particle hit, the film would develop. So what did he see? And this is kind of interesting. Actually, it's very interesting. Is that he saw that most of the particles passed exactly through, nothing happened. It looked like they didn't even hit the foil. This is the brightest spot right here. Most of the particles went straight through. Some of them were deflected. And some even bounced. And that was the most surprising of all. Because this is really pudding, and you're shooting essentially a cannonball into it. This is going to have an effect on it. You expect to see some of these divert, and you would expect to see most of them go straight through or kind of on the side. So, what can you conclude out of this? And usually if I lay it out this way, the data that's actually there, people have a lot of trouble with it. But if I use my superpowers, here we go. We're going to zoom in. So that this is my piece of gold foil. Look, that's the thickness of the foil. And these are my alpha particles. And I tell you that most of these alpha particles go straight through with no effect. You may have to slow it down on the video, but trust me, they're going straight through. What would you say is behind the box? Absolutely nothing. So, most of the particles pass straight through the atom. What was the assumption? It's mostly nothingness. Okay. All right. If, on occasion, the particles were to, say, go and bounce back, what would you say is behind the box and go off at all different angles? You would say something more massive than the ball, heavier than the ball, and something's there, like my coffee cup. All right. Experiment over. Some go through, some go through, and occasionally they hit stuff and they bounce right back. All right. Demo done. We're going to zoom back to normal person size. There you go, magic. All right. So Rutherford came up with the same conclusions. Most of it's empty, but when it hits something, boy, it really hits something. It's got a lot of positive charge, a lot of mass. So the positive charge and the mass is in one place. It's in the center. It's the nucleus, and the nucleus is small. Wait a minute. Nucleus is tiny. No, let's back up further. The nucleus is wicked, wicked small. If this was the nucleus, the atom would be the size of New York City. Or if you think about the Super Bowl and all of the paraphernalia with it, the parking lots, everything associated with the Super Bowl, the coin they flip to start the game, the coin's a nucleus, all of the other stuff associated with the Super Bowl is the atom. So it is small. However small you think the nucleus is, it is smaller than that. Okay, so what do we know? The negatively charged particle is called the electron. The positively charged particle is called the proton. And the neutral atom is called the neutron. All right, so for electron we use E, for proton we use P, for neutron we use N. As far as take-home message goes, I want you to know that electron has a negative charge and very little mass. A proton has a positive charge and 1 mass unit. A neutron has no charge, it's neutral, and has 1 mass unit. Let's delve into this a little bit more. They don't really have a mass of 1. They have a mass of 1.673 times 10 to the minus 24 kilograms and 1.674 times 10 to the minus 24 kilograms. You might notice that those masses are awfully similar, and to 3 sig figs we can call them identical. So, how many of you think well in 10 to the negative 24? Yeah, I don't either. But they are essentially the same, so we can call that 1 unit. And we can use a conversion factor, right? And that's an AMU. So that's what an AMU is. And we'll just say this is 1 AMU and this is 1 AMU, and we won't worry about the sig figs in the 3rd, 4th digit. And if we really look at the mass of an electron, I don't have it on the board, but you can look it up in the back cover of your book with the constants. It's about 1/2000th of an AMU. So you need 2,000 electrons, which no atoms have, or even close to even equal 1 AMU, and even then the atom would be enormous. So it's really something mathematically we don't have to worry about when we talk about the mass of an atom. Okay, so the electron, it has mass. I don't want anyone to ever say that an electron has no mass, because it doesn't. But it has small enough mass we can ignore for most calculations. And then the charge is the same thing. It's 1.6.02 times 10 to the minus 19 coulombs. They're both the same, so we just call that 1 charge unit, 1 atomic charge unit. We usually just drop that off and call it -1, -2, -3, +1, +2, +3. So, again, take-home message, electron has very little mass, negative charge, protons 1 and 1, neutron is neutral with a mass. So how do we put that in symbol form? EPN. At the top goes the mass, 0, 1, and 1. At the bottom goes the charge, -1, +1, 0. You have your symbols. Sometimes I'll do the shorthand. For electron, I'll just do E with a negative, and I circle the negative so you know it's not a mathematical symbol and it doesn't get lost. And P with a positive, again, I circle that so that doesn't get lost and you know it's not a mathematical symbol, it's a charge. And that is that. Very quickly, the atom. And no, I don't mean the DC superhero. I mean the chemistry superhero. Our smallest piece of material that retains the properties of the element. Okay. So, again, if we zoom in on the nucleus, wait, keep zooming, a little bit more. All right, there we go. All right, you're going to see the protons and neutrons are all in one place, they're all jammed in the middle, really, really small. The electrons are on the outside. So an atom's really small. You can't see it. Can't see it with a microscope. It's really, really small. Electrons are moving at, say, 1/4 of the speed of light. The speed of light, you can go from here, or wherever you're sitting right now, to Los Angeles and back multiple times in a second. So when you talk about where the electron is, as it moves around the nucleus, it can go to California and back in 1/10 of a second. It's confined to a really, 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 really small space. So what the electron is, we always talk about this as being nothingness and empty, but it's not. The electron's everywhere at once. It's smearing, it's blurring around. Think the Flash, if you want, to stick with the DC bad, pop culture references. It's blurring around. That electron's everywhere at once. So the atom, there's no way to approach an atom without hitting the electron. So the atom does feel hard, if you will, even though it's made of empty space. My hand is mostly empty space. This counter is mostly empty space, and no matter how many times I do this, I can never kitty pride myself through the table because the electrons are covering all that space at any given point in time. So we call this an electron probability, electron density cloud. We don't know where the electron is, but it's really carving out a surface and a shape at all points in time. And that is our view of the atom. Thank you for your time. Have a wonderful day.